Imagine a world utterly still. For centuries, we believed that if you cooled something to absolute zero, all movement would stop, atoms frozen in perfect silence. But nature is more mysterious. Even at the coldest temperatures, a secret, persistent motion remains. This isn't the jostling of heat, but a fundamental tremor, an impossible dance predicted by quantum mechanics. Absolute stillness, it turns out, is forbidden. The universe never truly sleeps. For years, this quantum dance was just a theory, impossible to see, too small and fast to capture. How do you film something so faint? The challenge was immense, like photographing a hummingbird's wings with a Stone Age camera. Yet, humanity's curiosity is relentless. Scientists set out to build a camera powerful enough to witness this impossible dance. It would require technology of unimaginable precision, able to illuminate and record a performance lasting less than a trillionth of a second. This is the story of that quest, and the breathtaking discovery that followed. We thought we understood stillness, but the universe had a secret. Even in the deepest cold, atoms vibrate with energy that can never be removed. This ghostly motion is woven into reality itself. For decades it remained hidden, a beautiful, unproven theory. But we are driven to see what's never been seen. And so, the impossible dance was finally brought into the light. To understand this story, we must revisit two competing ideas about the universe. Classical physics, the world of Newton, says that if you remove all energy, atoms stop moving, absolute zero is perfect stillness. But quantum mechanics, born in the 20th century, tells a stranger tale. At the smallest scales, certainty vanishes. Particles exist in clouds of possibility, not fixed positions. Even at absolute zero, atoms retain a tiny, irreducible energy, zero-point energy. Think of it as the universe's engine that never shuts off. The quantum rules say you can't know both an atom's position and speed perfectly. If it were truly still, its position would be smeared across the universe. So, atoms must always jitter a little, even in the coldest cold. Two stories, the classical silence and the quantum shiver. For a long time, scientists trusted quantum math, but longed for proof. The zero-point motion was subtle, too small and fast to see. Proving it would require a revolution in observation. The challenge: build a tool to catch a ghost. The quantum world demanded new ways of seeing. The search for direct evidence began. Could we ever truly witness the universe's secret tremor? The answer would change our understanding of reality. The main obstacle to seeing this quantum jitter is the Heisenberg uncertainty principle. Werner Heisenberg realized observing a quantum system changes it. To see an atom, you must bounce light off it, but even a single photon can disrupt its delicate motion. It's a cosmic catch-22. The act of looking destroys what you want to see. Imagine trying to photograph a dancer in the dark with a blinding flash. You capture a pose, but the flash startles the dancer, changing the next move. You can never see the original undisturbed performance. Scientists faced this problem with zero-point motion. Any light strong enough to reveal the atoms would overwhelm the subtle quantum jitter. The signal was drowned out by the noise of measurement. The uncertainty principle set a fundamental limit. For decades, the quantum dance remained hidden. Scientists saw hints of zero-point energy in materials, but not the motion itself. The dancer stayed in the dark. A new approach was needed, a flash so bright and fast it could capture the atoms before they reacted. The solution would require a flash of genius. The quest for the perfect camera began. The breakthrough came with the European X-ray Free-Electron laser, or XFEL, near Hamburg, Germany. This colossal machine stretches over 3 kilometers underground, a city-sized camera for the atomic world. Its purpose: create the brightest, shortest X-ray pulses ever made. These X-rays are 1 billion times brighter than conventional sources, crucial for seeing even a handful of atoms. But brightness isn't enough, speed is vital. The XFEL delivers femtosecond pulses, so brief light barely crosses a bacterium in that time. This combination of intensity and speed makes the XFEL unique. The femtosecond X-ray pulse acts like an unimaginably powerful flashbulb, freezing the quantum dance before atoms can react. Scientists now had their camera and their subject, a simple molecule, cooled near absolute zero. The experiment would use the XFEL's power to blast the molecule apart, hoping to capture the ghostly echo of the dance. The stage was set for a revolutionary experiment. The experiment was elegantly destructive. Scientists took acetylene, a molecule of 2 carbons and 2 hydrogens, cooled to just above absolute zero. At this temperature, only the 0-point shiver remained. Then came the XFEL's flash, a single ultra-bright, ultra-short X-ray pulse. The pulse ripped the molecule apart, stripping away electrons and causing the atoms to explode outward. This Coulomb explosion was key. The flying atomic fragments' paths revealed their positions and momenta at the instant of the flash. Sophisticated detectors caught these fragments, like analyzing firework debris to reconstruct the original shape. The explosion preserved a perfect memory of the molecule's state. By repeating this millions of times, scientists built a vast collection of atomic snapshots. Each captured a different phase of the 0-point dance. With millions of snapshots, the real work began. Digital reconstruction. Each explosion's debris was traced back to reveal the atom's positions at the moment of the flash. Like assembling frames of a movie, scientists built a statistical map of the atom's likely positions. The result, a 3-dimensional dynamic model of the molecule showing the quantum jitter in action. Hydrogen atoms vibrated and bent just as quantum mechanics predicted. The ghostly dance was finally caught on camera. This was a landmark achievement, directly observing the universe's restless heart. But the dance held a surprise. Scientists expected the atom's 0-point motions to be random and independent, but the data revealed something unexpected. The atoms moved together in coordinated patterns. When one hydrogen atom shifted, the other responded, a synchronized performance, not a chaotic jumble. The atoms were coupled, their jitters linked by quantum bonds. It was a carefully choreographed routine, not random flutters. This discovery showed the quantum world is more interconnected than imagined. 0-point energy drives a collective, coherent motion across the molecule. The dance was more beautiful and intricate than anyone had dreamed. The path to this discovery was not straightforward. The initial experiments confirmed 0-point motion, a huge success. But the deeper, synchronized dance was hidden in the data, overlooked at first. Years later, a fresh analysis revealed subtle correlations missed before. It took persistence, new tools, and a willingness to question old assumptions. The synchronized quantum dance was almost a footnote, nearly lost. But a second look turned it into the most profound finding of all. Discovery, it turns out, is as much about asking the right questions as having the right machines. Filming atoms in motion is more than confirming a theory. It opens a new era of control over the material world. Understanding the quantum dance lets us design new materials, improve quantum computers, and create better medicines. The techniques developed here can reveal the fastest processes in chemistry and biology. We've opened a window into the femtosecond world, once hidden from view. The European XFEL is a microscope for the 21st century. Our journey into the quantum realm has just begun. Each discovery reveals a universe more intricate and beautiful than we imagined. The dance goes on, and we're only learning the first steps.